Hello, everyone. Thank you very much for joining this recorded presentation of our project, WoodXZip project. My name is Yutaka Goto. I am a researcher at Chalmers University of Technology, and on behalf of our project team, I would like to give you a presentation about our project, which focused on real-life assessment of the moisture safety of a wall configuration under the Swedish climate. So this is the outline of my presentation here today. I would like to give you the introduction about the project background, so you are more familiar with why we did this project in such a way. And then I move on to the methodology of the project, real-world measurement of the hydrothermal performance of the wall at HSB Living Lab, and numerical modeling of the wall assembly performance. And then I would show you the results and discussion of those investigations, and I will briefly conclude the project in the end. So the introduction. We are seeing an increasing demand of residential units in the Swedish market. So we want to build more buildings because the demand is simply increasing. And at the same time, we are seeing the increasing interest in wood constructions because of its environmental performance. Wood grows, trees grow as they capture carbon dioxide from the atmosphere. And as long as we use wood materials in the material form, we can store the carbon in the tree bodies as a material, and we can contribute to the climate mitigation by doing so. So this is the basic reason why there's this increasing interest in wood constructions. And here I show you two small examples around HSB Living Lab. This is a student apartment in the Johanneberg campus of our university, Chalmers University of Technology. And it's a 6-story timber construction apartment. It's only, let's say, 3 minutes walking distance from HSB Living Lab, actually. And another one, this building is called a working lab, another multi-story timber construction, which is located actually right next to HSB Living Lab. So even within such a short distance from the Living Lab, we are seeing those new types of timber constructions. And when we talk about new larger timber constructions, we are seeing the increasing usage of this CLT cross-laminated timber as a load-bearing component. This is how it looks from its section. It's consisting of several layers of timber lamellas. So one layer is consisting of already some lamellas. The grain direction of this layer is this way. And if you look at the next layer, the grain direction is actually oriented in this way. So those lamellas are glued crosswise, and it creates a whole solid timber panel for the load-bearing function. I show you two examples of the CLT usage in Sweden. This is a residential building made of CLT near Stockholm. And this is another example, project which is currently under construction in the north of Sweden, Skellefteå. Once it's completed, it will be one of the timber high-rise buildings. I think it will be about 5 meter high or something once it's done. And the core of this high-rise part is made of CLT. This is a picture from last year. So the current construction should have proceeded much more than this picture. But as you can see, the core of this building is also consisting of such a material. And in our project, we want to use CLT. CLT is actually seen as a relatively expensive material compared to other wood-based materials. And what we want to work on is to reduce the cost of CLT constructions by introducing a simpler construction compared to what is done normally in the market. So a simple and cost-competitive construction method with CLT by applying an insulation composite. This is what we were interested in our project. And this insulation composite consists of two materials. One is MgO, magnesium oxide board, and the other one is PIR, polyisocyanurate insulation in a sandwich structure. This is how it looks. All the materials are white, so it might look not very distinct, but the two surfaces of this core insulation material, PIR material, is covered with this MgO board, and it creates this sandwich structure. And from this point on, I will call this a PIR insulation composite as PIC. In the past decade, there were some problems actually related to this MgO board. And there were some not very high quality MgO products which contain saturated salt in it, and it caused some serious moisture damages to buildings. But in our case, the MgO board that we used in this PIC was made sure that it is free of saturated salt problem. So we don't have to worry about this very peculiar particular moisture problem of MgO board. So the following is what we did in our project: development and moisture safety assessment of CLT and PIR sandwich panel under the Swedish climate, production of a full-scale wall mock-up and real-world testing under real climate. And this is where HSB Living Lab was a very essential part of the project. And validation of the numerical model for heat and moisture transfer in order to show that the wall is moisture safe under the Swedish condition. And finally, parameter study on moisture safety under various climatic conditions in Sweden. So this is what we did, and this is what I am going to show you in the following parts of the presentation. So, real-world measurement of the hydrothermal performance of the wall assembly. This is the sketch of the wall mock-up that we produced. One layer is consisting of 100 millimeter thick CLT panel, and the other layer is 136 millimeter thick PIC. And in our lab, we made them into one assembly of a mock-up sample. Very simple. And we installed this wall mock-up into the HSB Living Lab in Gothenburg, Sweden. The installation work itself took about 3 days, from 7th to 9th of January 2019. And I will show you some pictures from this installation process. As the first step, the exterior wall was removed from outside. So this is where this facade panel was removed, and the surface wind barrier is cut open, and this insulation sheathing is exposed. And after removing this insulation sheathing and the insulation with mineral wool, we can see it actually inside the room already. Once it was completely removed, this is how it looked from the inside of the room. So we installed our wall in this opening by putting some timber lamellas around the perimeter of this opening, so the wall mock-up would fit nicely into this opening. And yes, our wall was carried into the site, and with a crane, we put the wall into this opening. Of course, there is some gap between this wall mock-up and the actual opening of the HSB Living Lab wall. So we had to fill this gap by some insulation material and taping above it. This is how it looked like when we finished the ceiling by this tape and the insulation. And a new resident was going to move in this apartment shortly, so we couldn't leave it look like this, because I mean, this is not very pretty when you would see as a resident from inside. So we covered this mock-up wall with a gypsum board covering, which has some air gap between this outer wall of the original wall and this gypsum board covering. So the air between this outer wall and this gypsum board would be having the same condition as the rest of the room. So basically this wall under this was exposed to the indoor climate directly. So now I would like to talk a little bit about the sensors that we installed. One sensor was installed on the interior surface and another sensor was installed on the exterior outdoor surface of the mock-up wall. And we also installed 3 sensors between the CLT panel and the PIC. And this is how it looked like when we were installing it. So these are the 3 sensors, and those sensors were put right on the surface of the CLT panel, and it was covered with the PIC on top of it. The monitoring started on the 16th of January 2019, and the resident moved in on the 14th of February, and the measurement lasted about a year from there. And yeah, basically this is pretty much how we measured the humidity and temperature in the wall and outside the wall and also inside the wall. I mean, inside the apartment. From this point on, I am explaining the numerical modeling methodology. We used this one-dimensional transient heat and moisture simulation software to simulate the heat, temperature, and relative humidity in the wall under the given climate condition. And we also need to give the material data to run the simulation. So these are some selected data for the material properties of CLT and MGO and PIR. And this is how this one-dimensional wall model looks like in the simulation. This part here is the CLT panel with a thickness of 100 millimeter, and the insulation part is this 8 millimeter MGO on both sides of this PIR, which is 120 millimeter thick. And from this point on, I am looking at this monitoring position, which is the location where we could see the moisture accumulation most likely across this wall section. And in order to calculate the temperature and humidity inside the wall, we need to give the climate on both sides of the wall. In this case, I mean, this CLT side, this side is the indoor side, and this side is the outdoor side, and we need to give that climate there. And we measured the climate from the Living Lab testing. So we applied those measured climates directly. So this is the measured outdoor climate, and this is the measured indoor climate to run the simulation. And here I show you the results, and I give you some discussion together with it. So the comparison between the measurement and the simulation at the CLT and PIC border is what we are looking at. And this is the result of the temperature. This orange line is showing the simulation result, and those gray, yellow, and blue lines are showing the results from the measurement. And as we can see, all these lines are overlapping to each other. This shows that the calculation could predict the actual temperature values very precisely. And this is showing the relative humidity comparison, the same as the temperature. This is a simulation, and this is a measurement. And here we can see some deviation of the simulation compared to the other measured values. The calculation showed a more dynamic variation of relative humidity. And this is assumed that this is due to the lack of the moisture buffering consideration in this simulation software. However, the maximum difference between the simulation and measurement was 60.1%, and we would say this is an acceptable level of accuracy of the simulation, actually. And when it comes to the moisture safety of a wood construction, common reference value is 75% in order to make sure that there's no mold growth on the surface of wood. And we can see relative humidity at this risky point in the wall was always kept below 75% throughout the year. So we can say the moisture safety is guaranteed by this construction. But we have to say that this was constructed under dry construction. No built-in water was introduced because, yeah, we wanted to make sure that it will be most moisture safe. Now, I want to show you a parameter study which assumed that the CLT surface was wet during the construction time. So this would be the worst case scenario when we think about the moisture safety of such a wall. And in this case, the initial moisture content of the CLT was set at 25% based on some literature values, which looked at wet construction of CLT. And we run the simulation for a 5-year period under the Gothenburg climate, and this is a result. The red is the temperature, and blue is the relative humidity of the same location in the wall. And yes, in the beginning, the relative humidity is pretty high, and it takes really about 5 years to dry out this initial built-in moisture. And this makes us a little bit worried, like maybe there's a too long period of moisture humidity, actually above 75%. So we carried out the mold growth index analysis. This mold growth index analysis actually shows the mold growth, the level of mold growth on the surface of wood. And this is the result of this mold growth index analysis. Over the time, I mean, this green curve is the mold growth index, which is calculated based on both temperature and relative humidity for the same period. And this level 2 is the maximum acceptable growth level, where we could see several local growth of mold. It is visible only under microscopy. And based on this result, what we got was like, it was kept always below 2. Therefore, we concluded that even with a wet construction, the wall has a high enough drying potential to avoid severe mold growth in the wall. And this is the last parameter study where we looked at the various climatic conditions in different locations in Sweden, assuming a dry construction. 5 locations, Gothenburg, Stockholm, Lund, Karlstad, and Luleå was applied in this case. And I am showing the result from Gothenburg and Lund. Lund case showed the highest humidity in the wall, but there was no problematic moisture accumulation in this case either. So this is a relative humidity, and the highest was only above 50%. And again, our reference value is 75%. So it is way below the critical moisture situation for the wood. So even in the most humid case, we can say the wall can perform without any mold growth, moisture-related mold growth problems. So here is the conclusion. The comparison between the real-life measurements and the calculations showed very good accuracy of the simulation. A sufficient drying potential and low mold growth risk was shown by a parameter study which assumed a wet construction. The wall does not have a mold growth risk due to the accumulation of moisture under the climate of Gothenburg, Stockholm, Lund, Karlstad, and Luleå, which is west and east and south and middle and north of Sweden. And the wall can be used in Sweden widely with no mold growth risk, with the condition that the structure is not subject to a water leakage. And very importantly, it was essential to have the testing opportunity at the HSB Living Lab to demonstrate the wall performance. And yeah, if we would move on to further research and development of such technology, the cost effectiveness and the design of all the construction design details would be necessary for us to really think about the realization of such a technology. Here we would like to acknowledge Vinnova for the research fund and the Free Start Book for providing the CLT panel for the mock-up wall, and Tommy, our colleague, for the lab works, and most importantly, HSB for the cooperation in the test at the HSB Living Lab, and also the resident of the room for the installation of the test wall. And with this, I would like to thank you all for attending my presentation. If you have any questions, please feel free to drop me an email to this email address. Thank you very much.